In this video, we're going to talk about the complex trig functions. Let's start off with a little bit of review about real sine and real cosine. So the real valued and functions of a real variable that we know and love from like trigonometry and calculus. So I'm going to do these side by side. Sine's always in blue, cosine stuff's always in orange. The first thing, sine and cosine both take a real number and they send it to a number that is between -1 and 1. So it's a function that's onto that interval. I know that the absolute value of sine and cosine never gets bigger than 1, so it's always a number that's between -1 and 1 for all inputs. I know that sine and cosine are both periodic, and so sine of x plus 2k pi is the same thing as just sine of x, and cosine of x plus 2k pi is the same thing as cosine of x, and that works for all real numbers x and all integers k. I know that the x-intercepts of sine, those happen at integer multiples of pi. And I know that the x-intercepts of cosine, those happen at odd integer multiples of pi over 2. Here's another one that you might remember from, say, Calculus 2, or if you've taken real analysis, in which case you've probably justified this. I know that this sequence of polynomials here converges uniformly to sine of x. And in orange, I know that the sequence of polynomials, that involve alternating powers of even powers of x, and these even factorials, those converge uniformly to cosine of x. So sine of x and cosine of x are somehow these limits of these polynomial functions here that you've seen before. I know that both sine and cosine are continuous and differentiable. In fact, you could take their derivatives as many times as you want. You call those smooth. So they're continuous and differentiable for all real numbers x. And I know the formulas for the derivative. The derivative of sine is cosine, and the derivative of cosine is negative sine. And I know that sine is odd, meaning sine of minus x is the same thing as minus sine of x. And I know cosine is even, meaning cosine of minus x is the same thing as cosine of x. So I'm trying to capture some properties of symmetry between these two functions. And so there are the graphs of the sine wave and the cosine wave that, again, we should be very familiar with. Now, the real input x, that's an angle that's measured in radians. And so real sine and cosine, they have a geometric meaning that you probably talked about more in a trig class, where you draw the unit circle and you draw a triangle in there, and x is going to be kind of the angle that the x-axis makes with the hypotenuse of that triangle. And cosine of x then would be the ratio of the adjacent side of the triangle, or the adjacent side of the triangle, where I say adjacent, I mean adjacent to the angle x, divided by the hypotenuse of the triangle. And sine of x would be the side opposite the angle, divided by the hypotenuse. So I've got this nice geometric meaning for what real sine and real cosine represent when you think about the input x as radians. Now what we want to do is we want to try to define complex cosine of z and complex sine of z, where z is a complex number. But I want to make sure that this definition of complex sine and cosine matches real sine and real cosine whenever you plug in a real number. Now, a complex number z, that doesn't necessarily represent an angle, right? Z is probably not some angle in radians. Like what would 1 plus I be? I can't make sense of that in radians like I can just like x. So what that tells me then is that I'm not going to have the same unit circle triangle idea to help me think about what sine and cosine are. And so geometry is out of the question. So what we're going to do is we're going to take a more quote-unquote functional approach to trying to define this function. And we're going to leverage a function that we've seen before. So let's let theta be a real number. I know about the complex exponential. The complex exponential is defined as e to the I theta is cosine of theta plus I times sine of theta. And what I want to emphasize with my colors here is that cosine you see, that's just real cosine. You're plugging in a real number into cosine. Same thing, that's real sine. You're plugging in a real number to sine. So those are functions that I know tons about according to the review that we just did. And what else? Well, I could plug in minus I theta into this exponential, and I get this expression here. And I know that cosine of minus theta, I know that minus goes away. And I know that the minus inside sine of theta, I know that that comes out, right? That's using the even and the odd properties the even and the odd properties of cosine and sine. So that this green expression can be rewritten as just cosine of theta minus I sine of theta. And now what I'm going to do is I'm going to first add the pink and the green expressions together. And when I do that, I see that I sine of theta cancels. So I just get 2 cosine of theta, and let's solve that for cosine of theta. And so what we have then is another expression for real cosine in terms of this complex exponential function. Similarly, if I subtract the pink and the green expressions, so if I subtract the green from the pink, Then what happens? Well, now the cosines cancel. And I've already went through the trouble of distributing the minus sign of the green. And I get 2I sine of theta. Well, let's get sine of theta by itself. And I recover this formula for real sine. The real sine of theta is also, we can write it in terms of the complex exponential as well. So I've put these two formulas in a box. Real sine and cosine, they're considered as combinations of complex exponentials. Let's just extend this by replacing the thetas that were real numbers by complex numbers, z. So here's our definition of complex sine and complex cosine. Complex cosine is going to be e to the iz plus e to the minus iz divided by 2. And you can plug in whatever complex number you want into that. And complex sine is defined similarly. Sine of z is equal to e to the iz minus e to the minus iz, now divided by 2I, where again, you can plug in whatever complex number z you like into that formula. So we've achieved our goal of trying to define complex sine and cosine in a way that matches real sine and cosine. So what do I mean by that? If I replace z by theta, I just recover these two formulas in the boxes, and those are real cosine and real sine respectively. So whenever you plug in a real number into these yellow and purple formulas, you just get regular old real valued cosine and sine that we know and love. Now here's a question. If z has real and imaginary parts, x and y, so if z is x plus iy, what are the real and imaginary parts of these two functions, cosine of z and sine of z? So what I want to try to do is I want to try to write cosine of z in the form u plus iv, and then I want to try to write sine of z in the form u plus iv as well. And then that can kind of lead you to thinking about using some things you've seen before with u and v, like the Cauchy-Riemann equations. So that's maybe the direction that we're headed. So how are we going to do this? How do we pull apart cosine of z and sine of z? Well, the first thing that we need is to recall the real hyperbolic trig functions that, depending on your calculus class, I remember mine, we didn't really talk about it at all. I don't think I learned about the hyperbolic functions until I took a differential equations class. Anyway, you can always tell it's a hyperbolic trig function because there's an h after cosine or sine. Some people call this cosh, and some people call it sinh. I'm probably just going to say hyperbolic cosine and hyperbolic sine. Anyway, they look pretty similar to the formulas that we had above. Notice there's just no i's anywhere. So, and here again, theta is a real number. And so these, you can easily calculate values of these because you have buttons for these on like a calculator, like a standard TI calculator, or my favorite, like Desmos. If you go over to the little functions window, the hyperbolic trig functions show up if you scroll a little bit. So we can obtain values for these guys pretty easily. And so I want to keep these two formulas in mind, because what we're going to do is we're going to pull apart complex sine of z. So these formulas, again, to remind you, that are in pink here, so try to embed those in your brain, these two combinations of these real exponentials, because they're going to show up again shortly. So sine of z, what we wrote down above, is that should be the same thing as e to the iz, and here I'm replacing z by x plus iy, so e to the iz minus e to the minus iz over 2i. And what we're going to do is we're going to use some exponent rules. So the first one, if you distribute the I through the exponential part, through the power, you get e to the minus y times e to the ix. And then same thing, minus e to the positive y times e to the minus ix, all divided by 2i. And now what we'll use like Euler's formula to talk about what is e to the ix and what is e to the minus ix. So that's where we're able to bring in some cosines and some sines. And the way that this is written right now, all I'm going to do in the next step is rewrite it so that it's not the exponentials in front. Think about distributing the exponentials through and then recollecting the terms to try to get sine and cosine out front. So kind of distribute the exponential through, but then kind of refactor. And if you do that, you should come up with, well, sine of x times the first thing, I e to the minus y plus I e to the positive y plus cosine of x times e to the minus y minus e to the positive y, all divided by 2i. Next thing we're going to do is we're going to split up this fraction. So think about splitting the 2i, goes to each of these. And I can cancel the I in the first one. The I in the denominator cancels out with the I on the exponentials inside the parentheses. And on the other one, I'm just going to move, when I divide by I, remember that's the same thing as multiplying by minus I. So I hope that that explains why there's suddenly a minus I in front of cosine of x. And you should remember, these formulas in pink should look very familiar. Those are hyperbolic trig functions. The first one is hyperbolic cosine of y, and the second one is hyperbolic sine of y. And so what ends up happening, or actually there's a minus sign in there, sorry. So notice there's a sign change too. If you look a little bit closely at the hyperbolic sine one, And if I compare to the formula above, notice e to the positive theta, or just e to the theta is the first term there, minus e to the minus theta. If I go back to this pink line here in the middle, it's backwards. So that's why I hope you see that I've combined the minus sign in pink. And when those combine, that gives me plus this imaginary part. So what have we done? Hopefully I haven't lost you or confused you too much. I have managed to rewrite sine of z in its real and imaginary parts. So the real part of complex sine is sine of x times hyperbolic cosine of y. And the imaginary part of sine of z is cosine of x times hyperbolic sine of y. And so what does that allow me to do? That allows me to figure out, like, on a calculator, what would the value of like sine of 1 plus I be? Now I've got a formula that helps me do that. It helps me figure out what that complex number would be, what that complex output would be. And so just to recap, this is the real part of sine of z, and this is the imaginary part of sine of z. You can do a similar computation or a similar bit of algebra to try to recover the formula for cosine of z. And so the real part of cosine of z is cosine of x times hyperbolic cosine of y, and the imaginary part of cosine of z is minus here, sine of x minus hyperbolic sine of y. I should be careful, the minus sign is included in those when you talk about v. But like I said, now these formulas again are going to help you if you had to actually compute, what is complex sine of 1 plus I? What is that resulting complex number? It also helps you do things like find the zeros of these complex functions, because that's still something that, mathematicians were interested in. How do they behave? Now, what kinds of properties do complex sine and cosine have? Well, the first thing is they still satisfy this sort of Pythagorean identity. Sine squared of z plus cosine squared of z still gives you 1. So even though I'm saying we don't have like that unit circle triangle intuition for how to define complex cosine and sine, it still managed to satisfy this kind of remarkable property that I can't help but think about the unit circle with. And you could check that out. I'd suggest that you use the exponential definitions to try to see when you square those and add them together that you get 1. Sine of z and cosine of z are both entire functions. Remember, that meant that they're holomorphic everywhere or analytic everywhere. And the reason for that is because, well, they're sums and differences of entire functions. So e to the iz and e to the minus iz are both entire. So when you add them together or scale them by a complex number, you still get something that's entire. Now, what are the derivatives of complex sine and complex cosine? Let's take advantage of these new formulas in terms of the real and imaginary parts. For sine of z, say, we'll work through this one. So if I take the derivative of this function with respect to z, remember we saw in the video about the complex derivative and the Cauchy-Riemann equations is the formula for the derivative should just be, I'm going to take the partial derivative of the real and imaginary parts with respect to x. And so here's the notation for that. I'm using like the partial derivative symbol there. And when I do that though, the first one, I'm just going to differentiate sine of x because it's the only thing with an x, right? Hyperbolic cosine of y is constant with respect to x. So that just turns into cosine of x times hyperbolic cosine of y. And then here I get minus I times sine of x times hyperbolic sine of y. And if I look at that and stare at it long enough, I recognize, hey, that was the same thing as complex cosine. And so what we just showed is that the derivative of complex sine is still just complex cosine. And you could do a similar thing, and you'd see that the derivative of complex cosine still gives you minus complex sine. And so it's just like Calc 1. They still satisfy those same derivative rules. So even though I'm trying to emphasize that these aren't the same sine and cosine from Calc 1, they still satisfy the same properties. So in some ways, I'm trying to say to you that we've really just extended the definition of real cosine and real sine to the complex case. Now the sum, difference, etc. identities for trig functions, those still hold for the complex trig functions. So to give you an example of one, like when you add two angles together as an input of cosine, or in my case, not angles, sorry. When you add two complex numbers together, it still is going to satisfy that same formula that the real cosine satisfied when you added real angles together here. So it still splits apart this way. So if those bring back horrible memories of identities that you had to justify in a trig class, I'm saying that we still get all these identities for the complex trig functions as well. You might be wondering too, you've heard about other trig functions like tangent, say, or like secant, and we're going to define all of those in the exact same way. So complex tangent is still sine over cosine. Complex cotangent is still cosine over sine. Complex secant is 1 over cosine, and complex cosecant is 1 over sine. And these things, they all have the same like derivative rules, say, that you get in Calc 1. And that would be a good exercise to try to work through to try to justify. Sine of z and cosine of z, these are both periodic functions, and the period is going to be 2 pi. And here, you got to be careful. When it's periodic, it's a complex function, so like the period could be a real number, or it could be like an imaginary number. It could be like a purely imaginary number. And so just what does this mean as far as notation goes? I'll try to put a little bit more detail into what I mean. Sine of x plus iy is the same thing as sine of x plus 2k pi plus iy. So notice that like you can always add an integer multiple of pi to the real part, and sine will give you the same value. Similarly, the same thing holds for cosine. When you add an integer multiple of pi to the real part of your complex number, you'll get the same value when you plug it into cosine. And this holds again for all integers k. Now here's something that's weird. So far you've seen a lot of things that are like, hey, complex sine and cosine, they look like they work pretty similarly to real sine and real cosine. Here's one where it gets way different. The modulus of cosine of z and the modulus of sine of z, those are both unbounded. Remember in the beginning, I know that, well, it's never more than 1 in the real case. And so let me give you an example as to why. So if I think about the modulus of sine of z, remember that involves just squaring the real and imaginary parts, adding them together, taking the square root, right? Your distance from the origin, you think of it that way. So if I take the real part of sine of z, it's sine x hyperbolic cosine of y, I square that, plus I take the imaginary part of sine of z, it's cosine of x times hyperbolic sine of y, I square that, and then I take the square root. So I've got a formula here for what does the modulus of sine of z look like. I'm saying modulus, I call it, it's the same thing as absolute value depending on what book you're reading. And this on the right side, that's a function of 2 variables. So it's a real valued function as well, right? It gives you back a real number. It tells you like how far away from the origin you are. So I've got this function from R2 to R, and I can graph those things. I know its graph lives in R3. So what I'm able to do is I'm able to visualize how does the modulus of sine of z, how does the modulus of sine of z change? And here's the picture of what the modulus of sine of z looks like. So for whatever x, y you plug in, like the height, how tall this graph is going to be the modulus. And so something that I want you to notice is if you take y and you go either up the y-axis or down the y-axis, right? So if you move in the positive y direction or the negative y direction, you should see that the height, right, the sheet gets really, really tall. And so you're kind of going up along these parabolas if you go in either the positive y direction really far or the negative y direction really far. And so what that tells me then is that, well, you know, the sheet gets, you know, infinitely tall. And so that's trying to justify that the modulus of sine of z is unbounded. Something else that you can see in the picture is you see that the zeros of sine, you know, a function has a 0 somewhere. Well, that means that the modulus of the function has to be 0 there as well. And so when I look here, I see that the times that we touch the xy plane are at these multiples of pi along the x-axis. So sine of z has the same zeros as real sine of z does as well. So that's one last thing to take away from this little picture before I let you go.